The birth of light, when the darkness broke. Prologue, the silence before light. Before there was light, before stars painted the sky, before even atoms existed, there was a fire, not of flames, but of raw creation. The newborn universe was not silent, but deafening in its density. Time and space were entwined in a roiling dance of quantum uncertainty, a ballet of particles and energy, vibrating at the edge of existence. And yet, in all this motion, there was a kind of darkness. Not the darkness of night, for there was no sky. Not the darkness of shadow, for there was no light to cast one. It was a darkness of meaning, of separation, of chaos unshaped. This story begins there, in that hot, brilliant void, and follows the emergence of one of the most profound transitions the universe has ever known, the birth of light. Chapter 1, The Age of Fire. In the first seconds after the Big Bang, the universe was a blinding storm of particles, electrons, protons, neutrons, and photons. All trapped in a dense, hot plasma. Temperatures exceeded 1 billion degrees. Matter and energy were inseparable, constantly converting into each other. Photons, particles of light, filled space, but they were not free. They collided with electrons so frequently that they could not travel any distance. Light was trapped in fog. In this primeval furnace, time was not measured in days or hours but in fractions of seconds. Every moment brought change. The strong nuclear force fused protons and neutrons into light atomic nuclei, hydrogen, helium, a trace of lithium. But no atoms could yet exist. Electrons flew freely, constantly scattering light. This era is known as the plasma epoch. The universe glowed, but its glow was hidden, smothered by itself. Chapter 2, The Long Darkening. As the universe expanded, it cooled. Over hundreds of thousands of years, the seething fire began to settle. The temperature dropped from billions of degrees to millions, then to hundreds of thousands. Around 380,000 years after the Big Bang, a critical threshold was reached. The universe cooled to about 3000 Kelvin. At that moment, something miraculous happened. Electrons, which had long been bouncing freely, now moved slowly enough to be captured by protons. The first neutral hydrogen atoms formed. Helium, too, gathered electrons into its nucleus. This process is known as recombination, though it was truly the first combination of its kind. With no free electrons to scatter them, photons were finally free to move. This light, the cosmic microwave background, CMB, was released in all directions, spreading out as the universe expanded. It was the first light to shine freely across the cosmos. Ironically, this was also the beginning of a kind of darkness. With matter now electrically neutral and light decoupled, there were no new sources of light for hundreds of millions of years. The stars had not yet formed. The era that followed is called the Cosmic Dark Ages. Chapter 3. Light Fossil, the CMB. Today, that first light still travels through the universe. It has stretched and cooled over billions of years. What began as searing radiation has become a faint glow, detectable only by the most sensitive instruments. The cosmic microwave background is now just 2.725 Kelvin, barely above absolute zero. It is uniform in every direction, a nearly perfect blackbody spectrum, whispering to us from every corner of the sky. But within this uniformity lie tiny fluctuations, minuscule variations in temperature and density, 1 part in 100,000. These fluctuations are not noise, they are primordial fingerprints. They map the seeds of galaxies, the architecture of the cosmos itself. Discovered in 1965 by Penzias and Wilson, the CMB has become one of the most important windows into the early universe. Satellites like COBE, WMAP, and Planck have mapped it in exquisite detail, revealing a cosmic cartography older than stars. We are not just looking into the past. We are witnessing the moment when the universe first became visible. Chapter 4, The Great Silence. In the wake of recombination, the universe was filled with hydrogen and helium gas, cool, neutral, and quiet. No stars, no galaxies, no planets. The light of the CMB flowed freely, but it did not illuminate anything. There was nothing to reflect it, nothing to cast shadows. This period, called the Dark Ages, lasted for millions of years. Gravity began its quiet work, pulling matter toward regions of slightly higher density, the same ripples frozen in the CMB. These tiny imperfections, near statistical bumps in density, would grow under the relentless pull of gravity. Dark matter, invisible and abundant, provided the scaffolding. Normal matter followed its lead. But this process was slow. The universe was vast and expanding, its contents spread thin. Silence ruled, but not forever. Chapter 5, First Light. After hundreds of millions of years, the quiet gas began to collapse under gravity's pull. Clouds became denser, hotter. In the densest regions, pressure ignited nuclear fusion and the first stars were born. These stars, known as population 3 stars, were massive, brilliant, and short-lived. Composed almost entirely of hydrogen and helium, they blazed with intense ultraviolet light. For the first time since the CMB, new light flooded the universe, not the passive glow of a cooling fireball, but the active, energetic fury of stellar fusion. These stars changed everything. Their radiation ionized the hydrogen around them, creating glowing bubbles of plasma. Their deaths, in titanic supernovae, forged the first heavy elements: carbon, oxygen, iron. The Dark Ages ended not with a bang, but with billions of tiny flickers, the first stars piercing the dark like needles of light. Chapter 6, Reionization. As more stars and early galaxies formed, their ultraviolet light began to reshape the cosmos. This era, known as reionization, was a cosmic renaissance. Photons from these stars reionized the surrounding hydrogen gas, stripping electrons from atoms and turning the universe back into plasma, but this time, thin and diffuse. Unlike the opaque plasma of the early universe, this reionized gas was transparent. Light could travel, galaxies could shine, and the universe became visible across vast distances. Reionization was not instantaneous. It unfolded over hundreds of millions of years, like a fog slowly lifting. Patch by patch, the cosmos cleared. This transformation was profound. The universe, once again, became lit not by the residual heat of creation, but by the fusion fires of stars and galaxies. Chapter 7, Fossils of the Sky. Though billions of years have passed, the light from the time of recombination, the CMB, remains. It is the oldest light we can see, a fossil of the universe's childhood. Unlike light from galaxies, which can be blocked or redshifted beyond detection, the CMB is everywhere. It fills the universe like a ghostly memory. Modern instruments measure it with exquisite precision. The Planck satellite, launched by the European Space Agency, mapped the sky in microwave wavelengths, revealing the tiniest fluctuations in temperature, just microkelvins apart. These fluctuations tell a story of density waves in the early universe, of sound waves rippling through the primordial plasma, of gravity shaping the first structures. We cannot see beyond the CMB, it is the edge of our observational horizon, but within it lies the blueprint of everything. Chapter 8, Sound Before Sight. Before light could travel, sound did. The early universe was a dense, hot plasma, and sound waves propagated through it like vibrations in a drum. These waves, called baryon acoustic oscillations, arose from the interplay between gravity pulling matter inward and radiation pushing it outward. They left imprints in the distribution of galaxies, like ripples frozen in the fabric of the cosmos. Today, we can measure them not in sound, but in the clustering of galaxies across space. These echoes of primordial sound provide yet another way to probe the early universe. The light of the CMB shows us a snapshot, the sound of BAOs shows us the motion within. Together, they tell a story of a universe in motion long before the first star ever shone. Chapter 9, The Weaving of Galaxies. From the ashes of the first stars came the raw material for galaxies. Gravity drew these stellar forges together, forming swirling islands of light and dark. These early galaxies were unlike our modern spirals and ellipticals. They were chaotic, clumpy, and often violently merging. But over time, cosmic structure emerged. Galaxies spun themselves into elegant spirals, bloomed into giant ellipticals, and clustered into vast filaments stretching across space. Dark matter served as the cosmic scaffold. It did not shine, but it shaped. Like invisible architecture, it dictated where matter could gather and where voids would grow. The universe began to resemble the one we see today, a vast web of galaxies connected by gravity and history. Chapter 10: Echoes of the First Light. The cosmic microwave background is more than a relic. It is a message encoded in light, whispered across the ages. Every point in the CMB sky corresponds to a point in space 13.8 billion years ago. It's not just background noise, it is structure, frozen in time. The tiny variations in temperature and polarization across the sky hold information about the composition of the early universe, the geometry of space, the nature of dark matter and dark energy, the curvature and fate of the cosmos. By measuring these variations, we reconstruct the conditions of the universe mere hundreds of thousands of years after its birth. This is why we say we can still see the light from that moment, not with our eyes, but with instruments that turn microwave whispers into cosmic maps. Chapter 11: The Universe as a Telescope. Light is more than illumination. It is memory. When we look at distant galaxies, we do not see them as they are, but as they were, because light takes time to travel. A galaxy a billion light-years away shows us its ancient self, glowing from a time when Earth's continents were young. The farther we look, the further back we go. The Hubble Space Telescope, peering into deep fields, has seen galaxies as they appeared just hundreds of millions of years after the Big Bang. The James Webb Space Telescope, JWST, is now revealing galaxies even closer to the era of first light. We are building telescopes not to look farther, but to look earlier. To rewind the universe through light. Chapter 12: Redshift and Relics. The light from the CMB has been stretched redshifted by the expansion of space. What was once visible light is now microwave radiation. Redshift is not just motion. It is a record of the stretching of space itself. A photon that began its journey at 3000 K now arrives as a 2.725 K whisper. This shift tells us the scale of the universe at different times. It gives us the cosmic distance ladder, a way to measure not just how far something is, but when it is. CMB photons, redshifted by a factor of over 1,000, still carry with them the imprint of the very young universe, proof that space itself has grown. Chapter 13: The Last Scattering Surface. The moment when the CMB was released is called the last scattering surface. It is not a place, but a time, a boundary between opacity and transparency. It is the farthest we can see with light. No photons from earlier times can reach us. They were absorbed or scattered in the dense plasma. Beyond that surface lies a cosmic curtain, a horizon of observation. But the CMB allows us to see the universe as a spherical shell, 13.8 billion light-years in all directions, with Earth at the center of observation, not because we are special, but because we observe from here. We stand at the center of our own observable universe, and the CMB defines its outer wall. Chapter 14: The Symphony of the Cosmos. The early universe was not static. It pulsed, it oscillated. Like a bell struck in the first moment of time, it rang with patterns of sound and light. These patterns are etched in the CMB and in the large-scale structure of the universe. They are the chords of creation, the fundamental notes from which the universe composed itself. Scientists now use these harmonics, seen in both the CMB and the spacing of galaxies, to refine cosmological models. They reveal the universe's age, density, and composition with stunning precision. We are listening to a symphony 13.8 billion years in the making. Chapter 15: Light as Time. In everyday life, light moves so quickly we take its speed for granted. But on cosmic scales, its finite speed becomes profound. The light from the sun takes 8 minutes to reach Earth. From the nearest star, over 4 years. From distant galaxies, billions of years. So light becomes a kind of time machine. Looking far is looking back. And the oldest light, the CMB, shows us not galaxies or stars, but the raw fabric of spacetime when the universe was still in its infancy. Through light, we do not just measure time. We witness it. Conclusion: the light that connects us. From the fiery birth of the universe to the quiet glow of the cosmic microwave background, light has been both witness and messenger. It reveals the story of creation, carries the echoes of primordial sound, and bridges the vast distances of space and time. Though billions of years separate us from that first moment when darkness broke, the light-born then still surrounds us. It flows through every corner of the cosmos, whispering the secrets of our origins. As we continue to build ever more powerful instruments, to peer deeper into the night sky, we deepen our understanding of the universe not just as a collection of stars and galaxies, but as a vast, interconnected tapestry woven by light. In every photon that reaches us, there is a story of beginnings, of transformation, of enduring mystery. We are the inheritors of that light, the seekers who listen to its ancient song. And so the birth of light is not just a cosmic event frozen in time. It is a continuing journey, one that invites us to explore, to wonder, and to discover the infinite story written across the fabric of space and time.